essentially physics consists of two types of activities. One is the theory of physics and the other is the experiments. And so we generally call a physicist either a theoretician who works with paper and pen, or these days much more on a computer, okay, doing computations and simulations and formulating theories. That means formulating a set of ideas which can explain certain observations, and you can test the theory. On the other hand, there are experimentalists who work in the laboratory, like you will be having in the parallel course to this, and they perform experiments, they record data, they might make generalizations from their data to say it appears that this kind of trend is followed by my data. And the theorists need to take these observations and these experiments into account and explain them using their theories. So the two things move in tandem. Every time you have an experiment that maybe defies the theory, appears to break the theory, then you need a new theory which will explain the new results and explain all the previous results. So that's how the theory progresses. Whenever an experiment proves that your previous theory is incomplete or broken, it has to be modified. Equally, a theory may show that a certain result is expected from a certain experiment, but experimentalists may not have performed that experiment yet. Yeah? So not all instruments exist, not everything is possible for us to test. And theory gives us ideas for what kind of new instruments to make so that we can test new things. For example, you would have heard about the gravitational waves. This is a new experiment that became possible for physicists working in collaboration together because you need very sophisticated equipment. And they confirmed the existence of gravitational waves, which was something that the Einstein's theory had predicted long ago, but it had still not been tested for almost 100 years. So almost 100 years later, we found proof to validate Einstein's theory of gravitational waves. Okay. So let's look at some of these people, and this is the physics that we're going to be studying, some of it. We start with here, does anybody recognize this person? This is Sir Isaac Newton. In the 1600s in the UK, he performed a number of experiments. So he's an experimentalist, but he is also a theoretician of sorts because he developed a lot of mathematics. And that form of mathematics is called calculus. Okay. So he worked on things like optics, which you will do in physics too. And he worked on all of classical mechanics and gravitation. We will study Newton's laws. That's much of what you will study in this course. So it's called classical mechanics, the work that Newton did. And most of the length and time scales are what we ordinarily see. So what our eyes can perceive, the size of this table or the room, that would be the length scales that we're talking about. We're not talking about small atomic distances because we can't see them, okay? So classical mechanics does not apply to the realm of the very small, and also doesn't apply at very high speeds, the speed approaching the speed of light. That was shown by this man, Einstein, Albert Einstein. I'm sure all of you recognize him. Did his work in the early 1900s, okay, 1905, 1915. These are famous years when he gave his two theories of special relativity and general relativity, respectively. And he showed the limitations of Newton's work. Okay. Einstein was a theoretician. He never did work in the lab, but he always just used his brain, his mathematical ability, his ease of writing expressions, working stuff out, and that's how he came upon his ideas. Okay. Here we have an experimentalist, Marie Curie. You might have studied about her in chemistry. Okay. She studied a lot of radiation-related work. We'll be doing some of that in physics too. And you might study about her in chemistry, some of her work. Here's somebody who's actually alive today. I hope all of you recognize him as probably one of the greatest physicists on Earth today. This is Stephen Hawking. Works on astrophysics. Another aspect of physics, this has to do with the very, very large scale. So we're looking at to the edge of the universe. We're trying to understand stars and planets, any matter out there in the universe, matter that we cannot see. Okay, so we're trying to understand the structure of the universe and how it works. Going back in time, any guesses for who this is? This is Pythagoras, and we're going to see that work that he did in the BC is stuff that we still use today. So he's a Greek mathematician, if you like. In those days, there were no separation between mathematics and physics and philosophy. He gave his famous Pythagorean theorem about right triangles. And I want you to notice how often we use it. So although today it may seem like quite a simple concept, it's something that once you establish a fact, it never goes away if it's never disproved. So his ideas are still carrying on and likely to carry on forever as far as we know our understanding goes today. Here we have Archimedes sitting in his famous tub. That is where he got the idea of the Archimedes principle. We will study about Archimedes principle in this course, which talks about buoyancy, which means the force felt by an object when it's immersed in water. It's called the buoyant force, which is an upward force, like a thrust produced by the water, which makes a person appear lighter than they are. So there's an apparent weight which is less than your true weight. If you have been to the swimming pool, you would have noticed that you feel a lot lighter in the swimming pool. You're not carrying all your weight. It's the same concept. And here we have Johannes Kepler. We will also study his work on gravitation, and he showed mathematical relationships between the orbits of the planets and how far away they were from the sun, amongst other work that he did. So these are some of the great physicists. There's no way I can do justice to all of them. This was a random pick, mostly picked for their recognizability. I was hoping that you would recognize at least some of these people, and also picked for their relevance to our course. So our course is going to talk right from here, all through here, and up to Newton. That's where we stop, 1600s. In Physics 2, you will get some feel of the work of Einstein. Okay, so we'll move on from the 1600s to the 1800s to optics and electricity and magnetism.